Hello, this is section 3.2 for Calc Survey, and today we'll be expanding our derivative knowledge. And so last time we did really baby derivatives. We did if it's just a number, the derivative is 0. If it's a linear function, the derivative is the slope. If it's a power function, x to a number, you can pull the exponent down in front and subtract 1. So those are our very basic derivatives. And we're just going to add some more rules to those. So I'm going to convince you that there's really only two. Even though it looks like a lot of new ones, there's really only two. So so you'll notice e to the x, e to the u, a to the x, a to the u, all of those are pretty much the same thing. They're a number raised to a variable. U represents a function other than just x. So it could be 2x or x squared minus 3. But u is it's a function in terms of x. Okay, and then you'll notice all these are log functions. So see how you have one thing you're learning and then one thing you're learning. So even though it looks like a lot, it's not so bad. And then it builds. So if you have e to the x is the easiest derivative because the derivative is e to the x. That's it. It's just e to the x. I'll explain the times 1 here in a second. Now if it's e to the u is actually, it's the same thing, e to the u, just like we wrote e to the x, but then you have to multiply by the exponent. And u represents some function, so we'll just represent its derivative by u prime. So up here, e to the x was the same thing, just like we wrote here, but the derivative of x is just 1, because that's the slope of x, it's 1. So technically, you would just see e to the x, but we are multiplying by the derivative of the exponent, which is 1. Now, when it's a to the x, you have to do natural log of the base times the original exponential, which is what we did in the previous two. But what's the natural log of the base? What's the natural log of e? It's just 1, so we don't have to write that up here. So we are technically doing natural log of the base times the original exponential, but we just don't write natural log of e because it's 1. But if it's something other than e, you'll have to write natural log of the base times the original exponential. And then if it's something other than x, you'll have natural log of the base times the original exponential times the derivative of the inside. So you can almost think of e to the x as the easiest scenario, a to something other than just x as your most complicated scenario, but these are all technically the same. You do natural log of the base times the original exponential times the derivative of the exponent. That's the derivative of an exponential function. Okay, and I'm going to say that over and over again. Natural log of the base times the original exponential times the derivative of the exponent. That's how you do a derivative of an exponential. And I'll say that all the time. Okay, now logs, again, we're going to start with the most basic and we're going to build on that. So natural log of x, the derivative is just 1 over x. That's it. Now, natural log of u, remember u represents something other than just x. So it's 1 over u, just like we did a 1 over x up here, but then we have to multiply by the derivative of the inside. So you have to put u prime in the numerator. Now, if it's something other than base e, natural log is base e, but it's something other than e, then you'll have to do 1 over natural log of the base, just like that would have been up here, 1 over natural log of e, but that's just 1, so we don't write it. But 1 over natural log of the base times 1 over x. And then here's your worst case scenario. So it's 1 over natural log of the base times 1 over u times in the numerator u prime. So again, there's really just two that you're learning there. But you do need to learn these and you need to know them. Okay, so here's what some problems look like. So e to the x is just e to the x. E to the 2x, so here we have something other than just x, so it's e to the 2x times the derivative of the exponent, 2. Now in this case, it's going to be natural log of the base, so natural log of 1/4 times the original exponential, 1/4 to the x, and times the derivative of the exponent, but it's just 1. Log base 5 of x, it's 1 over natural log of the base times 1 over x, and since it's just x on the inside, the derivative of the inside is just 1. And you just got to get used to doing these. Now here's where they become a little more complicated. So e to the 4x to the 5th. So e is, remember, it's always the original exponential. There is that natural log of the base part, but natural log of e is just 1. So it's e to the negative 4x to the 5th times the derivative of the exponent. And you have to do the power rule. So pull that 5 down and multiply and subtract 1 from the exponent. The derivative of the exponent is always multiplied in the numerator. Okay, in this one, you have that 4, that's a scalar, but that's fine. You just leave scalars in front and multiply, and then do the derivative of what follows. Now here, notice the base is no longer e, so we have to put that natural log of the base part in there, times the original exponential, times the derivative of the exponent. Okay, here's a log problem. So it's 1 over natural log of the base, which is 10, times 1 over the argument, but then you have to multiply by the derivative of the inside. Not very happy with myself. We should really put this binomial in parentheses just to be a little more on the careful side. And of course, I condensed all this into one big fraction, but I don't want you thinking 2x is what we multiply this by, because really it's the quantity 2x plus 6. So Cogswell should have put parentheses there. All right, so 5 times natural log of x. When you do this derivative, it's 5 times, and then natural log of x turns into 1 over x. And then here, there's actually 2 ways to do this next one. You can approach it how it is and do 1 over x squared, but then times the derivative of the inside, so 2x, and then reduce. Or you could pull that 2 out in front, and then derivative of, it ends up being 2, and then derivative of natural log of x is 1 over x, and you get the same answer. It doesn't matter, because what you did was legal. So, all right, and then here's some applications for these problems. So the growth of a particular bacteria can be modeled by the equation. We've seen this, where T is the time in hours, P of T is the bacteria in thousands. How many bacteria will be present after 2 hours? Just plug 2 in, no calculus. But here comes the calculus. At what rate is the bacteria increasing at 2 hours? There's that instantaneous rate of change. So do the derivative. Oh, you can do the derivative now. 506 is a scalar, leave it in front. E is exactly the same thing times the derivative of the exponent. And since that's a linear function, it's just the slope. And once you have the derivative, now plug 2 into that derivative and you get the rate at 2 hours. So now you know that instantaneous rate of change at 2 hours. Isn't that cool? All right, and then find the equation of the line tangent to this graph at x equals 1. So we've done lots of tangent lines. You see tangent line, you need to think, I need a point and I need a slope. So plug the 1 into your function to get the point. That's your ordered pair. And then now you can do the derivative to get the slope at 1. So E is exactly the same thing times the derivative of the exponent. And we pull the 2 down, use the power rule. And then plug 1 into that derivative to get the slope, which is 2e. But then now I can write my equation. Y minus y1 equals our slope 2e times x minus x1. And you're done. So you've got to practice these. As you can see, they start to get a little more interesting. And as you can see, we're embedding the stuff we did in the previous section, where we're using the power rule, the slope of a line, and the derivative of a number. All that's embedded, and these derivatives are just going to keep building on each other. So you've got to make sure you're doing your homework and you're practicing, and you're starting to make sure you know how to use these derivative rules. Okay, so all right, email me if you have any questions.